0.4 times 2 times 10, so that's going to be 8. So we have the applied force is equal to 28 newtons. And so that's another example of something that may be on the exam. Even though it's very similar to the one that we did previous to this one, they both might make their way on the exam. That's entirely possible. So those two are, and what's nice about these is that they involve a lot of the things we've talked about. They involve position equations, velocity equations, finding how the forces, using the idea of the net force being what leads to the acceleration. Questions about this one? Okay, the last kind of one that we're going to do in just a moment here, we're going to look at something that an applied force on an object where gravity and possibly a normal force are involved, and we'll do things like finding its total acceleration vector. We'll find a free body diagram, including whether or not it has a normal force that's at work. And so, the last one, let's look at that. Okay, 5, 6, 7 here. Okay. So question 7, we have something like this. Let's have a mass. That's just going to be on a flat surface again. And now we have a force that's applied at an angle. That looks to be about, and it's easier if I use 30 degrees, so I'll just modify it a little bit and say it's going to be 100 newtons at 30 degrees. We'll have the mass be 5 kilograms, a little bit different than we did before. And we're going to say, okay, I won't break it down completely like this when I give it to you, but the overall objective is going to be to find the acceleration in polar form. But we'll kind of do several steps on the way. I might also ask you to say find things like find the normal force, find the y direction, and the x direction are not going to be equal. Find those two forces, and also find Phi and Fox, and also find, draw a free body diagram. So draw a free body diagram. And then I'll probably ask you to find this in XY form as well. And we talked about the 3 different cases that might exist. And there's only going to be an acceleration in the y direction when there is no normal force. Okay, so let's look at this. Okay, so we said that we can draw a free body diagram. There's Fax going in this direction, gravity going down, Fay in this direction, and a normal force maybe. And we said it depends on is Fay equal to or greater than the force of gravity? If it is, then the ground has nothing to do to push up on it. The applied force in the y direction would take care of everything. And so we can draw this. This is kind of a provisional drawing of it because we don't know if this will be longer than Fg or not. We don't know if there's going to be a normal force. We're just sort of guessing at things we know it might be there. Okay, so first thing, probably the best thing to do would be to calculate Fay and to calculate F sub g. In Fay, remember if you look at this, this is the triangle where this is Fax, this is Fay, this is 30 degrees, this is 100. We can say again, sine of 30 degrees, that's the opposite over hypotenuse, So we have 100 sine of 30 degrees. I didn't want this to be the case here. Okay, well, it's fine like this. Is equal to FAY. I'm not going to change the numbers here. So this is 50 newtons is FAY. On the other hand, FG is mass times gravity. We're going to continue to use our fiction that gravity is 10 meters per second squared. So we have 50 newtons as well. Well, what this tells us here, we can see that if we draw them side by side, the gravity pushes down. It's completely countered by FAY. That means that there is no room for the ground to push up. It has nothing to do, so the normal force is 0. What that also means is that there's no net force in the y direction. There's nothing left over. So that means that the acceleration in the y direction, in this case, is 0 meters per second squared. So we can say for this one, okay, now we can draw a better free body diagram. We can draw FAY going up, and it goes up in the same distance that FG goes down. You draw them proportional to their magnitude, and they're equal in magnitude. And FAX goes this direction. Since these two cancel, there's only acceleration in the x direction. And so we can say, okay, the acceleration vector is equal to AX, AY, and it's equal to the magnitude of A with the angle of A. Well, we know this is 0 degrees because it's all in the x direction. Since there is no y component of it, this will be equal to AX. Because remember, if we have, this is the value for it, you have AX squared plus AY squared. But since that's 0, since there's no net force in the y direction, that reduces to the positive square root of AX squared, which is just the same thing as saying AX. So right away we know that once we get AX, we have both acceleration vector in polar and xy form. So let's bring that over to here.
Okay, really quick, I have a question.
Oh, sure,
I'm
yeah.
sorry. When it comes back over here to the FAY, you put FAY equals to FG, which is equal to MG. How do you know FAY equals FG?
Oh, but because we calculated them both. I calculated FAY and found that it was 50, and then we calculated FG, which was M times G, and got the same 50.
Okay.
But you have to determine that.
Woo, so
That's a good question. If you miss that point, then it becomes,
I thought that was the cosine part. I thought we were finding the FAX.
oh, okay.
Because there's no
Okay, so-
FAX up there. Okay.
Oh, well, we haven't found it yet.
Okay, all right,
We're
that-
just about to do that, though.
Okay, okay.
Okay, so FAX, so now we need we need AX. And so to do that, we need the net force in the x direction, which there's only one force in the x direction, and so that is the net force in the x direction. In this case, we have no friction, so we need AX. And we know that the net force in the x direction is FAX because there are no other forces acting. And so that's equal to the mass times AX, to max. Okay, so now again with our, over here we have cosine of 30 degrees is equal to FAX times 100. So we have 100 cosine 30 degrees is equal to FAX. And that should be about 86.6 newtons. And so now we have what we need to solve for the rest of this. So we have 86.6 is equal to mass, which again, well, this time we chose 5, times AX. So that's going to be about 17.32. That's going to be our AX. So what that tells us is that our acceleration vector, tying it all together, is 17.32 with no component in the AY direction. and that's equal to, so its magnitude is equal to the same thing at 0 degrees with respect to the positive x-axis. Sometimes there'll be an acceleration in the y direction, but only when FAY exceeds FG. Then whatever's left over, that's used to accelerate the object. When FAY is less than FG, then there'll also be a normal force. You would have to include that on the free body diagram. So the only possible forces in the free body diagram are these right here, the two upward, the one downward. These two will always be a component of the free body diagram, as will FAY, but that status is provisional depending on whether FAY is less than FG or equal to or greater. Okay. Those are the questions that are going to be on the test with one possible unknown question. Are there questions about these? I mean, you've just gotten a bunch of them. Yeah.
Okay. Over here, where you get 86.6 equals 5AX,
Right.
is that 5 for the force? Or what's
Okay,
that
yeah.
5?
In other words, we calculated FAX.
Yeah, we got FAX, the 86.6, I got
And
that.
that's MAX. So this was the mass.
Okay,
Yeah,
that,
the
okay,
original mass, right.
okay.
Okay, so, if you have questions, I'll be here for a few minutes here, you can ask those, or wait till Monday. You'll have a chance, we'll probably have a test in the second half of the class, so you can ask more questions and maybe a little bit of new work. And if there are questions, I will definitely move to the second half of the class, because I want you to have a whole time to work on it.